the electric field due to the line charge. So meaning that any point surrounding this line charge is the objective here. You want to find the electric field at any point surrounding this particular structure. So when I want to solve this type of problem, I can see there's no indication of how we do it. So that's what in EMT, this is what students always face, meaning that they don't have ideas how to proceed. So for me, when I want to solve any EMT problem, I always try to make it simple by making it systematic. What I meant by that, the first thing that I always like to consider is to ask myself, what should be the applicable coordinate system that I should use to solve this problem? Okay, by choosing a proper coordinate system, we might be able to simplify the mathematical process of solving this problem. So we have three coordinate systems as what we have learned before: Cartesian, cylindrical, and spherical. By the nature of the field emitted by this structure, I can say to myself, the most logical coordinate system I should use should be cylindrical. So therefore, I'm going to say to myself, first, I'm going to choose cylindrical coordinate. Okay, so that what should be my first task whenever I want to solve EMT problem, to choose which coordinate system. So now I'm going to go to the second step. Since the field here have a cylindrical behavior pattern. So I know that in cylindrical, there are three variables, which are R, phi, and Z. So the next step, I'm going to ask myself, how do I arrange such that I'm going to reduce the number of variables in my problem? Meaning that instead of using all the three variables in my problem, I want to arrange such that I'm going to use only, might be one variable or two variables. So how do I do that? So logically, what I can do, I can place this line charge along the z-axis. By doing that, I'm going to eliminate the phi component in this particular cylindrical coordinate system. Due to that selection, what is it? By allowing the line charge to be on the z-axis of our cylindrical coordinate. Okay, with that have been decided, I'm going to go to the next step then. So I'm going to remove one of these as my second step. The third step is that I'm going to find the E. Okay, we know that since this problem must be solved based on continuous equation, therefore the equation of E of Coulomb's law that we have proved before should be defined as this equation: dq over 4 pi epsilon naught r square AR. So I have to solve this equation. So that should be the three steps I'm going to go through with you to solve this simple problem. And from the video that I attached regarding the application of this particular structure, you can see it can be used as the lightning rod for protection of building from lightning. So that's one of application that we can relate. So let's draw our problem now. So what we have now, we have cylindrical coordinate to be drawn. So I'm going to draw my cylindrical coordinate now. So first the z-axis. So this should be my x, and this should be my y. Okay, so let's make it clear. X, y, and z. Then, as we already decided, the line charge must be on the z-axis. So, but what we know, the length is h and is finite. So just to make it a bit nicer to be seen, I decide that my line charge should be on the positive side of the z-axis. Let's say from here, I'm going to draw, let's say, up to here. And the length of this line charge is denoted as h. Just to make it easier for labeling purposes, I'm going to say it's starting from A and ending at B. And I know that B minus A is equal to h, and this line charge has density rho L. Okay, so that's what I should do to agree with this. Point number 1, I'm choosing cylindrical coordinate system. Point number 2, to reduce the number of variables that I'm going to use for this particular problem. Okay, so I'm going to go for step number 3 now to solve the Coulomb's law equation. So from the equation, if you look properly, so I'm going to show you the equation now again. So this is the equation that we need to solve now. So I'm going to ask myself, how do I interpret the E? So that should be my first step in solving this problem. What should be the position of E in my diagram? Okay, so therefore, I'm going to just choose a point in space to help me to assume that position as our E position based on the equation. So I'm going to choose it to be, let's say, here. Okay, any point will do. It's not must be at what I shown to you here. It can be any point surrounding our line chart. But for the sake of making it nicer in my diagram, I choose the E position to be here. Then I have to link my E position with the coordinate that I'm using now, which is cylindrical. So which variable that we have to draw now? There are two variables, the R and the Z. So I'm going to draw the R for the E representation. So what should be the R? R should be the radius. So what does it will do? Must always make angle 90 degrees to the Z axis. This should be my R. And then how do I define the Z? The Z is the height from the where? From the XY plane. Okay, so therefore this should be the variable I'm going to use to represent my point E. Okay, so therefore I already defined the R, and then I define the Z, the height of the E point in my diagram. Okay, therefore this particular part of the equation has been represented in my diagram. So the next I'm going to do, I'm going to label this component now, my sample. Therefore, the sample must be taken at any point on the line charge. So I can choose it here or any point along the line charge. So again, I purposely choose my sample to be located up here. Again, I'm saying to you, you can choose this position to be anywhere along this line charge. Okay, so this sample now should carry a magnitude dq. So our sample always does this. It carries magnitude dq. Since the sample is not fixed, it can be varied at any point along this line charge. Therefore, I have to give the height of my sample now. Okay, because it's not fixed, so I have to label it properly. So I'm going to say to myself, so this height or this position based on the Z component of our cylindrical coordinate. So I'm going to give it as Z. But yet, this symbol has been chosen to represent the height of our E position. And from this simple diagram, we can see the height of the sample position is not the same as the height of the E positions. So to show the difference between these two heights, I'm going to choose my labeling for the sample position to be z prime. Just to show to myself, still depending on the z variable of the cylindrical coordinate, but yet it has different value compared to the z variable that we used before to represent the height of the E position. Therefore, I'm using the dash there. Okay, so therefore we have done the second step here, which is defining the position of the DQ on our diagram. So what next? So the next thing, I'm going to define the R and also the unit vector. Okay, so that should be the next step that I'm going to do. So therefore, how do I define the R, magnitude, and the unit vector? It's very simple. Okay, that can be done by joining the point, sample, and the E location. So this is what we're going to define as our vector R. Okay, so that should be our vector R. So vector R should be from the sample to the E location, and from the diagram. I'm not memorizing, I'm defining from the diagram. I can see this vector R can be defined by two components. One component is this vertical component, which is the Z component. Another component, which is the horizontal component, which is the R component of the cylindrical coordinate. So from the diagram, okay, I can see that the R vector now is equal to, okay, I'm going to choose this one first. Magnitude should be R. Coming out from the z-axis going to be defined as positive R. Then I'm going to define this vector. The magnitude now should be what? The magnitude should be this height minus this height. Should be what then? Yes, should be z prime minus z. Okay, that should be the magnitude because you are taking the difference between the sample height and the E position height. And now the direction should be moving downward because you can see from the simple diagram, the component of the vertical term must show downward direction. So must be negative z directions. So that's how we define the vector. Okay, therefore it's very important for us to draw clear diagram when we want to solve EMT problem. So then we can define now the magnitude simply equal to the square root of R square plus Z prime minus Z square. And the unit vector, okay, should be equal to the vector, then we divide with the magnitude. So what we're going to do now, we're going to define, therefore, okay, we can say Coulomb's law state now the vector dE must be equal to, okay, I'm going to choose my dq now. So the dq now should be equal to rho L dl, okay, because that is the model for line charge. And the dl here must link to this symbol. So this small length of this particular variable. Therefore, the dl must be represented by dz prime, because that represents the sample length and is linked to the height of z prime. So now my dE must take in this particular term, rho L dz prime. Okay, that should be done. And then the direction should be this one. Okay, I'm going to show the direction now. Okay, the direction should be R minus Z prime minus Z directions. Okay, divide everything. Okay, 4 pi, we'll make it 4 pi. It's a constant because we are assuming the medium is free space. Okay, so therefore 4 pi epsilon naught. And then the r term and the unit vector will give us now r square plus z prime minus z square, and then power of 3 over 2. Okay, that should be the mathematics of a DE, where at this particular position. Okay, so that should be the step we always do in a proper way, systematically. So what I have to do next, I have to find the total E. Okay, so total E now. Okay, electric field intensity so now the E should be equal to, so I'm going to take out all the constant now, rho L over 4 pi epsilon naught. Then I'm going to do the integrations. So I'm going to have now R direction minus Z prime minus Z directions. Everything I'm going to divide with R square plus Z prime minus Z square, power of 3 over 2. And now I'm going to look into my diagram to choose the limit. So I can see now the limit must be for the Z prime. Don't forget the dz prime now. We do the integration. Okay, the dz prime. So the sample now can move from A until B. So that should be the equation that I should solve. So what I'm going to do now, I'm going to go back to my textbook. If I open page number 122, okay, from the textbook now, because I need to solve this mathematics, I can see this table given to me. So the table said, okay, if I have this pattern of integration, say I have this pattern, let's say, x dx divide with, let's say, I have now a constant square plus, let's say, x square power of 3 over 2. So let's say I have that pattern. Okay, so the solution to that integration given by the table is equal to minus 1 over the square root of c squared plus x squared. Okay, that should be the solution to that integration. If I have another pattern, for example, let's say I have this pattern, so dx over c squared, c is the constant here, and then x squared 3 over 2, and then this should have solution given as the x divide with c squared square root of c squared plus x squared. Okay, so that's standard table given from on page 122 of our textbook. So if you have the textbook, you can open to that particular page and you can see the equation given for us to refer to in order to solve these integrations. Okay, rather than using a very complicated method to solve the integration, I'm going to use table here to solve the integration. Okay, so let's do that now. Okay, so let's do it together. So we have a constant now. So the constant is equal to rho L divided with 4 pi epsilon naught. So first I'm going to see there's R term there. So I'm going to say to myself, should be R. So R direction, R magnitude. So if I do this integration, I can see that is dz, okay? And then I'm going to, so it's going to agree with which particular set of equation. So the R term will agree with this particular equation. Do we agree on that? So let's carefully, yeah? Because there's no Z term on the upper part of the mathematics. So therefore I'm going to choose, there's no X term here, so therefore I'm going to choose this as my agreed solution. So what I'm going to do, okay, so this one should be our Z minus, so Z prime minus Z. Okay, that should be the X. I'm going to divide everything, so my C now should be the R, so therefore R squared, square root of R squared plus Z prime minus Z squared. So the limit of the integration from A to B. Okay. Now the next one should be minus. Okay, I'm going to have minus now. So Z direction, I'm going to put it there, Z direction. So now this term is appear on the upper part of the mathematics. Okay. So I'm going to say, okay, this particular Z component will agree with the first set of the table equation. Okay. So therefore I'm going to say should be equal to minus 1. I can see minus there. Divide with the square root of R square plus Z prime minus Z square. Then the limit should be from where to where? From A to B, should be close bracket. So that is the solution after the integration, but we are still not finished yet because we have to substitute now. Therefore, which particular term here need to be substituted with the A and the B? So, from the mathematics, we know that it depends on the Z prime. So now I'm going to say, okay, in terms of mathematics now, the E now should be equal to rho L divided with 4 pi epsilon naught. Okay, so first, I'm going to have the R term. Then I'm going to see from this simple mathematics, this R term can be cancelled with this R. So I'm going to have over R. Then I'm going to substitute now. So I'm going to first substitute which term? B. So Z prime with the B. So therefore should be B minus Z divided with the square root of R squared plus B minus Z squared. So that should be the first substitution. Then I'm going to substitute with the A. I'm going to minus again. So I'm going to substitute Z prime with the A. So A minus Z. I'm going to divide everything now with R squared plus A minus Z squared. I'm going to close the first substitution of R component. Then I'm going to go on with the Z direction. So I'm going to see now the negative going to become positive now. Okay. So again, I'm going to substitute properly 1 over the square root of the first Z prime need to be substituted with the variable B. So R square plus B minus Z square. Okay, done. Minus 1 over square root of R square plus A minus Z square. Okay, close bracket and then close bracket. So that should be our solution. Okay, so that should be our solution for the electric field, okay, generated by the finite line charge. So is it quite lengthy, the solutions? The answer is yes. So can we make it simpler? Yes, we can do it. So let's do it then. So let's make it simple rather than very long solution that we have here. We try to make it simple. Hopefully from the simple solution that we're going to create, we can memorize. So it's easier than try to solve every time when we are dealing with finite line charge. We have to do this lengthy process. So why not we develop a simple set of equation that we can memorize whenever we deal with this particular problem. We just recall that equation and we substitute with values. So therefore it's much convenient for us to do. So let's do it now. Okay, so how to make it simple? Okay, so let's draw the problem in 2D now. Okay, so let's draw in 2D. Two-dimensional, what I mean by that. So before we draw everything in 3-dimensional, so try to make it simple by redraw the same thing in 2-dimensional. So what we have? So we have here, okay, so let's say this is our x-axis coming out from the paper. Okay, to the right is the y-axis. And going up here is our z-axis. Oh, so you can't see it, sorry, yeah? Okay, now you can see it. So what happened to the video? Suddenly everything blur. Sorry about that, maybe red color, they can't see properly. Okay, so that should be our new 2D diagram of our problem. So what we're going to place now, our line charge located where? On the z-axis. From where? From A until B. Then, how do I draw the E position now? So the E position is actually a position having R value from the z-axis and making height z. So I'm going to redraw my E position to be, let's say, here. Okay, so what this E position has, first, the height is given by the z. Second, distance from this particular z-axis is equal to R. So that should be our E positions. Okay, in 2D here. And then angle here, 90 degrees. So now we're going to add extra information on our diagram by drawing the limit now. What I meant by that, I'm going to draw the limit where the charge starts. So I'm going to link to the position of E. So this is my first limit I'm going to introduce. And the angle given by this angle I'm going to denote as alpha 1. So alpha 1 is the angle between the line where the charge starts until the R value, or the line making angle 90 degrees to our line charge. So that should be the first new information I'm going to add in our 2D diagram. I'm going to add another line, which is where it ends, the line charge ends. I'm going to add this. So now I'm going to define this angle as alpha subscript 2. Okay? So now let's give label to the length of the triangle now. So we ask ourselves, what should be the length of this side of the triangle? Okay, from the diagram we can see, should be what then? Should be B minus z. Do we agree on that? B minus z. So what should be the length of this side of the triangle? Logically equal to, yes, should be equal to z minus a. Okay, so how about this length? What should be the length of this side of the triangle? Based on theorem Pythagoras, should be equal to the square root of r square plus b minus z square. Okay, and finally, this particular side of the triangle now should be given as r square plus z minus a square. So we already label all the relevant side of our triangle. So this is the two-dimensional representation of our line charge. So what I'm going to do next, I'm going to link this diagram to our solutions. That's what we're going to do. We're going to link the diagram to the solutions. So first I'm going to look at the first term now. Okay. Sorry about the mess. I'm going to adjust nicely so that you can see how do I link the solution that we developed together with the triangle. Okay, so let's do it now. So I can see from the triangle, I'm going to focus on the red box here. So let's make that comparison now. So I can see b minus z on the diagram is equal to this component of the triangle. Okay, and then the r square plus z, b minus z square, I can see this side of the triangle. Therefore, I can replace the lengthy equation with very simple trigonal equation. This side of the length divided with this length, in trigonometry we call it to be sine angle. And sine of what? Alpha 2. Okay, so that's done. So now instead of these lengthy equations, I'm going to replace the whole equation with the sine alpha 2 based on this triangle. I'm going to do next part of the r component now. I can see here for this particular box now, it's slightly different between the equation given in the box and the label, the symbol given in the triangle. What is the difference? Here is a minus z, but on the triangle is z minus a. So therefore we need to adjust slightly. So to do that, what I'm going to do now, I'm going to change the negative here to become positive, so that the term in the bracket now is becoming negative and positive. Now it's agreed on the symbol given on the triangle. So now it's becoming z minus a. So that representing this side of the box divided by this term. So for us, a minus z square is actually the same as z minus a square. So does not matter. So therefore I'm going to straight away say this should be equal to sine alpha 1. Okay, that's done. So now it's becoming simpler now. Instead of very long equation, we can see just two terms, sine alpha 2 plus sine alpha 1 for the r component. So I'm going to repeat the same with the z component now. So what I see here is 1, but I cannot see 1 on the triangle. So, but I can see here there's r there. So I want to use that in my mathematics. So I'm going to replace the 1 up here with the r. So for me to do that, I must divide the z direction with the r. Then only the mathematics becoming valid. So if you compare the altered equation with the triangle, you can see this particular component can be replaced with the cos alpha 2, agree? Okay, and then this one should be substitute with cos alpha 1. So now you already simplify the solution that we developed before based on the triangle that we drawn on the 2D model. So now I'm going to change now the long equation with this simple equation where when we have a finite line charge problem, the standard solution going to be E equal to rho L divided with 4 pi epsilon naught R, and then what we're going to have, the R component, and then sine alpha 2 plus sine alpha 1 plus the Z component, cos alpha 2 minus cos alpha 1. Okay. So that should be the simplified version. So what we have done, we have converted the long equation that we obtain for finite line charge to become a very much simple versions, but this equation must be used together with the triangle. Okay, so therefore with that we have set 2 equations now. Okay, so let's go back to our first problem that we set here. So let's see now, since this particular line charge is not on the z-axis, is actually in more general position. Okay, so how do I adapt the model that we assume along the z-axis to be applicable for this particular cases? Okay, do this equation still valid on this condition? The answer is yes. So let's do that, but with slight adjustment. So therefore, let's do it together now. So let's see now, this is the line charge in general position. I want to determine the E at this position. So whenever we deal with finite line charge, if I want to use this set of equation, I must be able to draw the triangle. So therefore, I'm going to define clearly now. So this is our E position. I need to draw a line to the line charge. And this line, I'm going to define to be perpendicular to the line charge. I'm going to define that as my R. General R. I'm not defining it as our R before, because these are based on cylindrical coordinate. So these are just the length joining the sample line charge, the line charge into the E position, making angle 90 degrees between each other. Okay, then I'm going to develop this particular limit. I'm going to say this to be standard alpha 1. So in this particular, I'm going to define to be alpha 2. So therefore, the equation that we defined before can be used. What is it? The E here, okay, I can say to myself now the E is equal to rho L divided with 4 pi epsilon naught. Okay, Then I ask myself the R. I'm going to see. So no more small r now. I'm going to put capital R. Then I'm going to see this should be close bracket. You just want to see, okay, open bracket now. I'm going to make it clear. Okay, so like this. So I see here R. R, as you can see now, based on cylindrical, is indicate to me that R is along these directions. So this unit vector making what to my line charge? Making 90 degrees. So I'm going to call this to be perpendicular component. So I'm going to call, instead of R here, I'm going to find unit vector which is perpendicular to what? To the line charge. That should be my next substitution here. Instead of R that we defined before, this is valid for cylindrical cases where we purposely place the line charge along the z-axis, and we can see the direction here obeying the r component of the cylindrical coordinate. So now we know that this direction must be following this path, and this path always making what angle to the line charge? 90. So I'm going to call it to unit vector which is normal to the line charge. Apart from that, everything remains the same. Sine alpha 2 plus sine alpha 1. So that's done. Okay, then we go to the next step then. So plus, I'm going to put plus. So now we're going to see there's a z direction. Z direction for us is following this particular movement along the z-axis. Or in other words, this direction is parallel to the line charge. Agreed? This direction is normal to the line charge. This direction is parallel to the line charge. So I'm going to say now, instead of z direction now, this should be unit vector parallel to the line charge. Now, apart from that, everything remains the same. Cos alpha 2 minus cos alpha 1. So therefore, that should be the more general representation solution for the E due to line charge at any position. Okay, so you have to adapt it slightly so we can use this equation. So therefore, life become easier. Okay, so therefore we have done this problem with quite a clear approach. So if you refer to our handout number 4, page number 2, so you can see there's a section on page number 2 which define electric field intensity of a line charge. So this is what we are dealing now. So actually the equation, the problem that we are solving before or solving now is the same as the question number 1 here. But the only different question number 1, the position is defined to us. Okay, so meaning that you have a line charge which is finite distributing along the z-axis. Okay, so therefore, so this question purposely mentioned the position, whereby on our problem that we solved just now is based on our interpretation. So we are dealing with very open-ended problem. So that's actually the case you always face in real engineering problem. The dimension is given, but how you solve the problem is not clearly stated. Okay, so now I'm going to continue. So let's do one more problem. I assume that you can see the logic now. So let's do one more problem just to make it continuous. Okay, let's do a problem now. So problem number 2 now. Okay, so refer to handout number 4. Okay, problem number 2. So let's do it now. Okay, I'm going to read the problem now loudly. So the problem number 2 states infinite. So now we have the term infinite. Okay, infinite. So no more finite, is infinite. So it's still a line charge having density 5 nanocoulomb per meter, so that should be our rho L, lie along the x-axis and the y-axis in free space. So find the electric field intensity, let's say at 0.005. So first, let's define infinite line charge solution before we do that problem. Okay, let's go back to our solution based on finite line charge. So let's see, for infinite line charge, what will be the solution that we're going to have? So for infinite line charge, we can define now the A position should be located at minus infinity. So we need that very, very far down here. So what happened to the angle alpha 1? So now we're going to see that this line is going to be parallel to our line charge. Therefore, we can see now angle alpha 1 is becoming 90 degrees. Okay, so, and for the case of limit B now, what happened to this limit B for infinite line charge? And we can say that the B now should be assumed to be located at plus infinity. And what happened to the angle alpha 2? Yes, alpha 2 now is becoming 90 degrees as well, due to infinite line charge pattern or behavior. So when we substitute this value into our solution before based on finite, we're going to see that it's going to be a standard solution or very peculiar solution which state that should be equal to rho L over 2 pi epsilon naught r in r directions. So what we can say, when you have infinite line charge, the only component of the field generated is the one orthogonal to the line charge. Only this term appear to be existent, and the parallel component going to be eliminated due to the infinite nature of the line charge. Okay, so this should be your standard solution representing infinite line charge problem. Okay, come back to our model now. So we have two infinite line charge. One is located along the x-axis, and the one is located y-axis. Okay, find the electric field at 0.005. So I'm going to do the part A. Hopefully you all try to do part B just to test your understanding based on the same process. Okay, so let's do for part A now. I'm going to use other paper now. Okay, question number 2. Okay. Z-axis, x-axis, y-axis. Okay, x, y, and z. Okay, the first line charge along the x-axis, I'm going to draw along the, so I'm going to draw black color. So this should be representing my first line charge. Since it's infinite, I'm going to add the dotted line. So this should be my first line charge. I'm going to call it to be rho, let's say x now. Okay. So that should be representing my first line charge, the value given to be 5 nanocoulomb. Okay. The second line charge I'm going to draw is on the y-axis, blue color, also infinite. So also infinite. So I'm going to draw it. Okay, dotted now. Okay. So that should be my second source, rho L y. So what we have to do then, we have to first, for the A part, find the E at the location 0, 0, 5. So 0, 0, 5 is on the z-axis, so it should be this one. Okay, so that should be my first, the position where you want to find the E. Okay, 0, 0, 5. Okay, first I'm going to solve for the infinite line charge on the x-axis, black in color. So this is our line charge. This is where I want to find the E. Because the line charge is infinite, the E must always make an angle 90 degrees to the line charge. Therefore, what I can say now, to produce that 90 degrees, the E must obey this pattern. So this should be my E for the infinite line charge on the x-axis. Y is making angle 90 degrees. Okay, so I'm going to call this to be my EX. Okay, just to show the relation. So this should be my EX component. So I think, sorry, E rho L X is easier. If not, we're going to confuse with the E component X. So that should be my solution. Very simple. I don't have to solve it mathematically. I can just use the interpretation based on the graphical representation. So therefore, what I can conclude now, my E rho Lx should be equal to the rho L, should be rho L subscript x, divided with 2 pi epsilon naught. Okay, and then the R. What should be the R? The R is the distance between the source to the position where you want to find the E. So the R should be equal to 5. So how about the direction now? The direction must be unit vector. Okay, from the diagram, the direction should be agree with the Z direction. See how simple you can do when you actually, the graphical presentation is very helpful for us to use to make it simpler. So that should be the solution for the infinite line charge on the x-axis. So you can repeat the same process with the infinite line charge on the y-axis, where you can see it's also equal to the same solution now, because the rho L is the same. So rho Ly, I'm going to put here equal to 10 pi epsilon naught, also in the Z direction. So therefore the solution is E must be equal to the E rho Lx plus E rho Ly. So therefore that should be your final solutions. Okay. Inshallah, is it easy? Inshallah, it's easy. I'm sure you can feel EMT not that difficult, not provided you use proper method. For me, in this case, I'm using nice picture, clear picture to help me to interpret the problem better. Okay, shall I do one more problem then regarding line charge issue? Okay. Okay, so I'm going to solve another problem now, also from the handout, but slightly different in nature. Question number 6. Okay, we're going to solve question number 6. No more straight line, now the line having different shapes. So let's go into question number 6 now. What does the question say? Find the electric field intensity, still the E vector, on the axis of the circular ring of uniform charge rho L and radius B, assuming that the axis of the ring is along the z-axis. Okay, so that should be question number 6. So I'm going to draw my axis first, just to make sense. So what I have here, I have z-axis. I'm going to draw as x, and this should be my y. So what's stated by the question that the axis of the ring must be along the z-axis. So it doesn't mention in detail the actual position of the circular ring. Just mention the axis. So therefore, the axis must be on the z-axis. So to make this mathematics a bit easy, I'm going to assume now the ring actually residing on the xy plane. And the axis of the ring is along the z-axis. So therefore, I'm going to assume it to be on the xy plane. It's not mentioned by the question. I just assume it to be so, because I want to make the solution a bit easier. So the radius given, so the radius of our ring is equal to P, and then the density is given as rho L. So that's given by the question. Okay. So now you want to find the field. Okay. Find the electric field on the axis of the circular ring. So meaning that we have to find the electric field on the axis of the circular, meaning that on the z-axis. So that's what the question asks us to do. So let's do it systematically. First, which coordinate system that we should use here? Okay, because the shape of the ring is circular here. So therefore, I think the best coordinate system should be cylindrical. That's done. Then I'm going to define where is the location of my E. So the question clearly states E should be on the axis of the ring. So I'm going to make clear where is my E position. Okay, that should be my logical step after selecting the coordinate system. Where is the E? So the E is here. The third step, I'm going to take sample. So I'm going to take sample. So the sample must be on the source. I cannot choose the sample here because there's no source here. I cannot choose the sample to be located here because there's no source there. The only place I can choose should be on the line chart. So this representing my sample. Okay. So my sample now is DQ. I know based on the model of line charge, the dq must be equal to rho L dl. Then, based on my model mathematics and handout number 2, the dl that I'm going to substitute must be represented by the change of the phi angle. Therefore, we know that that should be known as the radius, P multiplied with the d phi. Okay, that should be the mathematic to represent my dl, to show the variance of angle phi. So we know that based on cylindrical model that we learned in handout number 2, this term of change of angle should be represented by this mathematics, should be radius multiplied by the change of angle. The radius is b, change of angle d phi. So that should be our dl. So what's next then? Yes, The next step is for us to join this point together. So this should represent our vector R. Okay, and based on the diagram, our vector R should be equal to horizontal component. What's the magnitude? Good, B. So it's moving towards Z direction. Based on definition of cylindrical coordinate, should be negative R. Okay, that should be the horizontal component of vector R. Then it's going to move upward. So plus, what should be the magnitude now? So let's see the magnitude here. I'm going to make it to be Z. Okay, just give the height to be Z. So Z and Z directions. So that should be my vector R. Horizontal component, B minus R. Vertical component, Z positive Z. Okay, so I can define my direction magnitude. R should be equal to the square root of B squared plus Z squared. So my DE now. Okay, so the DE should be equal to, based on our Coulomb's law equations, dq. So dq should be rho L, B d phi. Okay, that should be our dq. Okay, I'm going to divide everything with 4 pi epsilon naught. Then I'm going to add the direction now. So the direction should be first the vector B minus R plus Z, okay, divide with the magnitude, so therefore should be equal to B squared plus Z squared power of what? 3 over 2. Okay, so you can see it's repetitive again. It's exactly the same as what we have done in our first problem, line charge. Okay, so now I can see mathematic wise the DL term based on angle. Okay, no more length, it's angle, so I have to choose the limit properly. So therefore my E, I have to integrate the DE, but the limit chosen here should be angle. So phi from 0, because it's make complete circle, should go to 2 pi. Okay, so if you solve the mathematics, you can get it to be the E finally. Okay, the E solution there is equal to rho L. Okay, then I can see something interesting now. Something interesting is happening now. Okay, so I can simplify further due to the symmetrical properties of this particular source. What I'm going to do now, I'm going to choose opposite sample position. Initially, we choose the position of sample to be here, and then I'm going to choose the opposite sample position, which is to be here. So red in color. I can see now this sample also going to produce its own field. Agreed? Okay. So let's recall the black component first. Okay, the black component, we can see the E actually can be split into this component and the horizontal component. Okay, so that should be our black component. And the same thing that we can see now for the red component, we can split also into two, the vertical component and the horizontal component. So when I integrate, I'm summing the black component of field with the red component of field. By doing so, I can see clearly one of the component of the field going to be cancelled out. Which one that you can see from this simple diagram? Okay? Yes, the R component. The R component will be cancelled out because of the magnitude same, but the direction are opposite to each other, and yet the Z component will remain in the final solution. So therefore, I can straight away say to myself, the final solution only consists of the Z component, the Z directions. Then I'm going to say rho L, B multiplied with the Z, I'm going to have BZ now. Okay, B multiplied with the Z, BZ, divide with, okay, integration 2 pi and 2, I'm going to have 2 epsilon naught. Other than that, remain the same, which is B squared plus Z squared power of what? 3 over 2. Okay, and then what we can put unit now, it can be Newton over Coulomb, or we can choose the unit to be volt over meter. So up to you. There are 2 units that you can choose to represent our E field. Newton over Coulomb, remember when we define the E, force divided by the charge, or later on we're going to prove to us the unit also can be represented by volt over meter. So the unit can have either 2 representation. So therefore this should be our final solution that we're going to talk about for line charge. Okay, in my next session I'm going to solve problem, or we're going to solve problem based on surface charge sources. So with that, thank you very much for your attention. So hope to see you again in my future video. Assalamualaikum warahmatullahi wabarakatuh, and take care.